Hello and welcome to the Screencast on introducing R. In this screencast, we're going to talk about two related issues. One is how to generate regular sequences or to repeat sequences over and over again, both of which we will want to do. And the second thing is we're going to discuss and introduce some ideas of how we index objects in R, which is slightly different than say, languages like C, C++, and Python, although only a little bit different. So it takes a little while to get used to, but it's actually quite typical for programming languages that are thinking about data first and foremost. So first, let's think about regular sequences. Obviously, we might want to create a regular sequence, like a set of numbers from 1 to 20. This is so commonly done in R that R actually has a couple of useful shortcuts to do that. So if you just want to create a regular sequence of integers that are in intervals of 1, say just the numbers 1 to 20, you literally can just use a colon here between the numbers. So this will create a vector of numbers from 1 unto 20. So you'll see 1, 2, 3, 4, 5, 6, 7 all the way up to 20. And you can easily do the reverse. So 20 to 1 is literally just starting with 20 and going to 1. Well, that's very convenient. However, often we want to create more complicated sequences. And so that colon is just, in fact, a shortcut for using the sequence function. And that's just seq here. And there's a number of ways of using it, and I highly recommend if you have to create a lot of regular sequences that it's worth learning, reading up on the help files. But at the simplest, we can do something, say, going from equals 1 to equals 20 by 0.5. So instead of getting 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on all the way up to 20, we're going to get 1, 1.5, and so on all the way up to 20. We also don't need to, it's worth getting to know that you also don't need to actually specify that from, to, and by. As long as you call the function, the arguments in the right order, it will assume you mean whatever that regular order is. So since from is the first thing in the function, it will assume that that 1 right here means from, this means to, and that equals 0.5. And at least in the Mac GUI, one of the convenient things you'll often see, is if you call a function, you'll see down here sometimes some of the options for it, although in this particular case it doesn't have it for sequence. If people want to use the RStudio, which is a sort of an integrated environment for R, it also allows you to do this quite easily. Okay, so we'll work in class on doing a couple of things. We'll make sequences from, say, -1 to 10 as an example, so you may want to think about that. So in addition to creating sequences of regular numbers, sometimes we want to have a particular number and repeat it many times. So let's say we want to repeat the number 2 20 times. Well, the rep function will allow you to do that. In this case, we're just going to repeat 2, and we're going to do it 20 times. And if we do that, our vector of many 2 should be 22s. And we can, of course, check the length of that. And indeed, it is. And we can actually combine this with this. Doesn't need just to be numbers. We can do this just as well for characters. So if we go many A's, indeed we see a whole set of A's. We can combine this, say, with our regular sequences of numbers. So if we want to create, repeat the numbers 20 through 1 twice, we can just go 20 colon 1 times, say, times equals 2, all within the rep function. As we see, we go count down from 20 to 1, and then again it repeats 20 to 1. And quite easy to use this in a variety of ways. Again, I highly recommend you take a look at some of the intricacies of the rep function and look at the help there to see many of the other options that you have. We can repeat, as you've seen, although this is calling a vector directly. If we want to repeat the numbers 1, 2, and 3 times, we can just call it like this. Obviously, there'd be a simpler way of writing this, but this works just fine. Okay. And this actually can become very helpful when you're generating data that has particular levels. It's particularly useful for certain types of simulations, as we will see. So imagine we want to create a factor, where we have 2 different types of water, lakes and rivers, and we want to create data associated with it. So we're going to have 5 observations that are of lake and 5 different observations that are river. And we're going to use those for a simulation. Instead of having to go lake, river, lake, river, lake, river, or lake, 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 river, 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 we just might want to use the rep function to do this. And we just go each 5 times, and then you see lake happens 5 times, river equals 5 times. If you want it to be lake, river, lake, river, lake, river, you could use rep, make the vector lake and river, and just say times equals 5, and then that would provide the alternative way of doing this. We can also use this to create matrices. Let me clean the console window. So say we wanted to create a matrix where we're repeating 20 to 1 4 times, and we're going to want it in a matrix format. We could do it like this. So here we've got a matrix of 4 columns, and each column goes from the number, each row of that matrix has the same numbers going from 20, 19, and so on and down. All these sorts of things make a lot of mathematical computation and things that we're going to do for statistics and simulation much, much easier. And we'll do some exercises on this as well. Finally, for this these first screencasts I've done are all sort of representative from the first introductory script that I've written, the R introductory tutorial part 1. But one of the most important things you can learn in R is how to use indexing in R. And indexes are called using square brackets. And we've seen this before. So when we have A is, say, 1 to 20, we call A, as you might remember from, I think, the first or second screencast, that first number here, that 1, represents the index. That's saying this first element here, this number 1, it's the first element of that vector. And if we created a much longer vector, let's create a vector now from, say, 1 to 100, so it goes across multiple lines, you'll see that the first 27 elements of this are all in this first line, 1 through 27. The 28th element also happens to be the number 28, and that's the 28th element, the 55th element, and so on. And just so maybe it's a little less confusing, let's do it in reverse. Clear this up. Take a look. So the first element here is 100. We count backwards. The 28th element of this vector A, is the number 73. The 55th element of this vector is 46, and so on. And of course, this last element would be the 100th element. We can always check that by just using length, and indeed, length 100. So why do we need to know this? Well, one thing we may want to do is when we have a vector like A, we might go, oh, hey, I just noticed that one of these, maybe this was data we collected, but one of these elements is actually incorrect. This number here, this first element, 100, is actually supposed to be 135, is what we actually observed, or something like that. And if we want to do that, then we can, first of all, look at that first element. A1 is 100, and we can do that for any element here. So we can do that for the 20th element, and so on. But we can also change that element. So if we want to change that first element of A, let's change it to 200. If we did that, and we now look at our vector A, we'll see that the first element is now 200. So we can actually change in place, and this is unlike, again, some programming languages, we can modify the variable in place and modify elements of that variable in place, so we don't have to overwrite or create a copy to do so. We can also extract multiple elements, so let's say we want to extract several elements of A. Let's say we want to get the first, the third, and the fifth element of A. We'll get, as we see here, 200. The third is 98, and the fifth is 95, as we'd expect from up here. And we can combine calls using the indexing with other things, and this is in fact one of the greatest uses of it, with regular sequences. So maybe we want to extract the last 10 elements, or only the first 10 elements of A. So one thing we could do is say, let's grab A, but we only want the first 10 elements. So we can just go 1 to 10. And here we'll get a new vector that's just the first 10 elements of that original vector A. And of course we could save that as, let's just call it new A. But it's even more powerful than that. Obviously we can also do subtractions, and I should mention that first. Say we want to remove the very last element of A, but keep the first 99 in place. And this is a little bit different than Python, and I have some more notes at the bottom of this script. what many people will expect would be looking from the back, but this is actually just going to remove, it's going to keep A in place and just remove the last element of this. And the use of this and the way this is used, while seemingly different from other languages, will become apparent over the weeks to come. We can also use this to extract particular elements that fit a certain value. So say we only want to extract elements of our vector A, or we'll create a vector B in this case. I don't know if we have one. Nope, we have a short vector T, B. Let's say we want to extract elements of the vector B, but only where B is greater than a particular number. So let's say we only want B where it's greater than the value 5. So obviously this element, and this element, these first three elements are not greater than 5. Only the last three elements is. So what this should select out is just those last three elements. So that will just give you the elements where the values of B are in excess of 5. So essentially what that does, if you think about B greater than 5, you do that, it's just creating a Boolean, so a true-false statement. And basically, wherever it's false in the index, it's basically excluding it. Whenever it's true, it's including it. And that's a very, very useful thing. You can do that not just for simple Booleans like that, but you can actually say, how about when, extract all elements of B where B is greater than 20, but less than 80, for instance, and maybe you have some data and you know that outliers are less than 20 or greater than 80. That would be a good example of doing this. So with that, and we'll go through some exercise with that, indexing for matrices obviously is equally important, so let's create a couple of matrices. We're going to go, C is going, before we create C, let's go with A. It's going to remove A. Let's remove B. Let's just create a new A. I know I could have just overwritten them, but I'll just make this. And then the create C is just going to be the sum of A plus B. Now we want to create a matrix, which we'll just call Q matrix. And that's just going to bind together. We're going to column bind vectors A, B, and C. And let's just take a look. So our Q matrix is just a 3x3 matrix in this particular case. And what I want you to notice here is our index now has these commas. And what that represents is rows first, then the comma, and then columns. So the first row is this. The second row is that. Third row is that. So that's referring to rows. So if we go Q matrix and go 1, we just get the first element of that matrix, in this case a vector. Similarly, we could ask, okay, well, we just want the first column of this, or let's just do the second column, which would be 7, 6, 5. So we just go for column 2, and there we go. We get a vector for the 7, 6, 5. And it can be as simple as that. And obviously, you can extract particular elements. If we want to have the middle element, which is this 6 here, we can just ask for element 2, 2, and grab it that way. Now, if you do length on our created matrix here, it's going to give you something that perhaps you're not so interested in. It's going to give you the total length of the whole matrix, so the number of elements, just like we saw before, either for vectors of numbers or vectors of characters. It's telling you the total number of elements here. What it's not telling you is, say, how many rows or how many columns. The way to do that is quite simple. You can actually just go nrow, or ncol. In this case, it's a 3x3 matrix, so that's pretty straightforward, and that's pretty easy. There's also the easier function, just dim, for dimensions, and that will give you both rows and columns in order. And that now allows us to extract elements, and of course with Q matrix, if we wanted to change, let's see what it looks like again. Say we realize that element here, this 10, really should be an 11. We can go Q matrix. That's going to be the second row and the third column. Oops. And we're going to just change that to 11. And Q matrix we'll now just have an 11 in that place. And obviously we can have larger dimensional arrays beyond just a two-dimensional matrix, although in this class we'll mostly just deal with 2D matrices. But it can be just as simple as that. And I won't go through it here, but we can also pull things out by the name. So if we did this here, well, we might as well just call it since we're already here. This will actually pull out the vector, in this case column C. So we're still looking for column, but instead of asking for column number equal to 3, this column actually already had a name because of the original vector we used, which was called C, and so that pulls out the C column. I won't go through this in the screencast, but for those of you who are coming from other programming languages like Python, which I know many of you have used for previous classes, I would suggest taking a look below. I give some other examples about how not only indexing is different and indexing characters and what have you can differ a little bit, but some other questions that may help you, and some other sort of slightly more advanced programming things that we won't use in this class very much, but may be useful to you. Thank you.